Right now, every breath you take exists because of an accident. Earth sits in a cosmic sweet spot so impossibly narrow that moving our planet just 5% closer to the sun would boil the oceans into vapor. 5% farther, and the atmosphere would freeze solid and fall as nitrogen snow. We live on a knife edge suspended in a universe that actively tries to kill anything that moves. But Earth is not the standard. Earth is the fluke. In the darkness between stars, astronomers have discovered worlds so hostile that they redefine what the word dangerous can mean. Planets where the sky rains molten glass sideways at 5,000 miles per hour. Worlds being eaten alive by their own suns, screaming X-rays into the void as they die. Ocean planets with no land, no oxygen, crushing pressures that would compact your body into a sphere the size of a marble in less than 1 second. These are not theoretical nightmares. These are real places. We have measured them, we have watched them, and every single discovery forces scientists to recalculate how many ways the universe has invented to annihilate life. What you are about to hear will change how you see the night sky, because those distant points of light are not beacons of hope. They are tombstones marking failed experiments in planetary formation. They are warnings written in physics and fire. Prepare yourselves. We begin. In 1995, two Swiss astronomers pointed a telescope at a star called 51 Pegasi and discovered something that should not exist: a planet. But not just any planet. A gas giant larger than Jupiter, orbiting so close to its star that it completed a full year in just 4 days. The surface temperature exceeded 1,000 degrees Celsius. The atmosphere was being stripped away in real time by stellar radiation. The world was dying as they watched. Michel Mayor and Didier Queloz had just confirmed the first exoplanet orbiting a sun-like star. They expected to find distant, cold worlds similar to the outer planets of our solar system. Instead, they found a cosmic aberration: a hot Jupiter, a planet that violated every model of planetary formation that existed at the time. The discovery did not just expand our catalog of worlds, it shattered our understanding of what planets could be. Before 1995, humanity had only studied 8 planets, the ones in our solar system. We assumed they represented the standard template: rocky planets close to the sun, gas giants farther out, a predictable, orderly architecture governed by gravitational dynamics and the condensation sequence of the protoplanetary disk. 51 Pegasi b proved we were cosmically naive. In the decades since that discovery, astronomers have confirmed over 5,300 exoplanets. Each detection requires extraordinary precision. Planets do not emit their own light. They are invisible against the blinding glare of their parent stars. Finding them requires 3 primary methods, each more ingenious than the last. The transit method works like watching a moth pass in front of a streetlight. When a planet crosses between its star and Earth, the star's brightness dims by a fraction of a percent. The Kepler Space Telescope used this technique to discover over 2,700 planets by staring unblinking at 150,000 stars for 4 years straight. The dimming pattern reveals the planet's size. The frequency of dimming reveals its orbital period, but the method only works if the planet's orbit happens to align perfectly with our line of sight. Most planets remain invisible because they orbit at angles we cannot detect. The radial velocity method measures the wobble. Every planet exerts gravitational pull on its star. As the planet orbits, it makes the star dance in tiny circles. This motion shifts the star's light spectrum toward blue as it moves toward us and toward red as it moves away. The Doppler shift. By measuring these spectral shifts with precision down to 1 meter per second, astronomers can detect planets they cannot see. The technique works best for massive planets in close orbits because they cause larger wobbles. It struggles with Earth-sized worlds at Earth-like distances. The direct imaging method photographs planets directly by blocking the star's light with a coronagraph. This technique only works for young, hot planets that still glow with the heat of their formation. The vast majority of exoplanets are too faint and too close to their stars for direct imaging. But when it works, the results are stunning. Actual photographs of alien worlds hanging in the darkness. Each method has limitations. Each method introduces biases. The planets we discover are not representative of all planets. They are the ones we can detect. Hot Jupiters dominate the catalog not because they are common, but because they are easiest to find. They are large, they orbit close, they create strong signals. This observational bias means that the exoplanet catalog reads like a cosmic horror anthology. We are not finding pleasant habitable worlds because those are nearly impossible to detect with current technology. We are finding monsters, extremes, planets that push physical laws to their breaking points. And when astronomers compile lists of the most extreme exoplanets, a terrifying pattern emerges. The universe has weaponized planetary formation. It has created worlds that exist solely to demonstrate how many ways matter can be tortured. The definition of a dangerous planet depends on perspective. Dangerous to what? To human life, certainly. But more fundamentally, dangerous means physically extreme. These are worlds where the environment is so hostile that the planet itself becomes a weapon. Some dangers are thermal. Planets tidally locked to their stars with permanent day sides heated to temperatures where rock vaporizes. Permanent night sides frozen to near absolute zero. The temperature gradient creates hypersonic winds that never stop screaming. Some dangers are gravitational. Super-Earths with surface gravity 3 times stronger than Earth. Standing on these worlds would feel like carrying 2 of yourself on your back. Your heart would struggle to pump blood upward. Your bones would compress under loads they never evolved to handle. Walking would become an exhausting nightmare. Some dangers are radiological. Planets orbiting flare stars that randomly unleash bursts of X-rays and ultraviolet radiation strong enough to sterilize entire hemispheres. Or worse, planets orbiting dead stars. Pulsars, neutron stars that spin hundreds of times per second and blast their planets with focused beams of lethal radiation. Some dangers are chemical. Atmospheres made of vaporized metals. Clouds of silicate particles. Rain composed of liquid iron or sulfuric acid. Air so toxic that a single breath would corrode your lungs from the inside out. Some dangers are tidal. Planets in elliptical orbits that experience varying gravitational stress as they move closer and farther from their stars. The flexing generates internal heat through friction. Volcanoes erupt constantly. The crust never solidifies. The surface is a churning ocean of magma that renews itself every few million years. And some dangers are existential. Planets being consumed by their stars. Worlds in death spirals. Their orbits are decaying. Every year they move closer to the stellar surface. In a few million years, they will be swallowed completely. They are watching their own apocalypse approach in slow motion. The 5 planets we are about to examine represent the extremes of these categories. They are not just dangerous. They are fundamentally inimical to anything resembling life as we understand it. They are laboratories where the universe tests the limits of planetary survival. HD 189 733b, the glass rain world. Celts 9b, the planet hotter than most stars. Corot 7b, the lava planet with a disintegrating atmosphere. WASP 12b, the planet being eaten alive. And PSRB 1257+12, the pulsar planets, worlds orbiting a cosmic lighthouse of death. Each of these worlds was discovered through meticulous observation. Each discovery involved years of data collection and analysis. Each one forced astronomers to expand the boundaries of what they believed planets could endure. The instruments that found these worlds represent the cutting edge of astronomical technology. Ground-based telescopes with mirrors 10 meters across. Space telescopes operating in infrared and ultraviolet wavelengths blocked by Earth's atmosphere. Spectrographs sensitive enough to detect color shifts caused by velocities slower than a walking pace. The high-accuracy radial velocity planet searcher, known as HARPS, installed on the European Southern Observatory's telescope in Chile. It measures stellar wobbles with precision of 1 meter per second. It has discovered over 130 exoplanets. The Transiting Exoplanet Survey Satellite, TESS, launched by NASA in 2018. It monitors the brightness of 200,000 stars, searching for the telltale dimming of planetary transits. It has found over 300 confirmed planets and thousands of candidates awaiting verification. The Kepler Space Telescope, which operated from 2009 to 2018. It stared at a single patch of sky in the constellation Cygnus for nearly a decade. It discovered the planets are common. The galaxy contains at least one planet per star on average. 200 billion stars means 200 billion planets minimum. But quantity does not equal hospitability. Most of those 200 billion worlds are hostile. Most orbit too close or too far from their stars. Most have atmospheres too thick, or too thin, or too toxic. Most have no solid surface. Most are locked in orbital resonances that create eternal day and eternal night. Earth is not the template. Earth is the outlier. The concept of the habitable zone, the region around a star where liquid water can exist on a planetary surface, sounds reassuring. It suggests that nature provides safe harbors for life. But the zone is narrower than most people realize. For a star like our Sun, the habitable zone extends from approximately 0.95 astronomical units to 1.37 astronomical units. Earth orbits at exactly 1 astronomical unit. The margin for error is tiny. And being in the habitable zone guarantees nothing. Venus orbits at 0.72 astronomical units, technically near the inner edge of the zone. But a runaway greenhouse effect turned Venus into a hellscape with surface temperatures of 470 degrees Celsius and atmospheric pressure 90 times greater than Earth. The zone is necessary but insufficient. Mars orbits at 1.52 astronomical units near the outer edge. It lost most of its atmosphere billions of years ago when its magnetic field collapsed. Solar winds stripped away the air. The surface pressure today is less than 1% of Earth's. Liquid water cannot exist in open air. It boils instantly in the near vacuum. So even in our own solar system, only 1 planet out of 3 in the habitable zone actually harbors life. The success rate is 33%. And that is in a system we consider relatively stable and normal. When astronomers search for exoplanets in habitable zones, they find worlds that technically qualify but remain horrifically dangerous. Tidally locked planets where one side cooks and the other freezes. Planets with eccentric orbits that swing wildly between scorching summers and frozen winters. Planets with no magnetic fields, exposed to stellar radiation. Planets with thick atmospheres that trap heat, making the surface hotter than the equilibrium temperature would suggest. The hunt for dangerous planets is not intentional. Scientists do not set out to find worlds that want to kill us. But the physics of planet detection and the statistics of planetary formation conspire to fill our catalog with nightmares. Close-in planets are easier to detect, they transit more frequently, they cause larger stellar wobbles, they have stronger thermal signatures. So our sample is biased toward hot Jupiters, hot Neptunes, and super-Earths on tight orbits. These are the most dangerous categories. Giant planets on distant orbits take years or decades to complete a single transit. We have not been searching long enough to detect many of them. Earth-mass planets in Earth-like orbits cause brightness dimming of less than 0.01%. They require years of continuous observation to confirm. We have only recently developed instruments sensitive enough to see them. This means our picture of the exoplanet population is incomplete. We see the giants and the extremes. The quiet, stable, Earth-like worlds remain mostly invisible. They exist. Statistical models suggest they are common. But they hide in the noise of our data. So when we compile a list of the most dangerous planets, we are also compiling a list of the most detectable planets. The two categories overlap almost completely. But that does not make these worlds any less real. They exist. They orbit real stars. They have measurable properties, and they demonstrate that planetary systems can evolve along pathways that produce environments utterly lethal to anything alive. The 5 planets we are about to examine were chosen not for sensationalism, but for their extreme, verified properties. Each one holds a record. Hottest, fastest winds, highest radiation, most doomed. Each one teaches us something about the range of planetary possibilities. Each one serves as a warning about cosmic hostility. As we tour these worlds, remember that every measurement comes from real observations. The temperatures are calculated from spectroscopy. The wind speeds are modeled from atmospheric dynamics. The radiation levels are estimated from stellar properties and orbital distances. These are not fiction. These are data points in humanity's expanding map of cosmic hazards. The universe is not empty. It is full of worlds. But most of those worlds would destroy us in seconds. 63 light-years from Earth, in the constellation Vulpecula, a blue dot hangs in the darkness. From a distance, it looks peaceful, almost Earth-like. The cobalt hue suggests oceans and atmosphere. It suggests water and sky. NASA released an image in 2013 showing this world as a pale blue sphere. And, for a brief moment, the public wondered if we had found a second Earth. We had not found a second Earth. We had found a vision of hell wearing Earth's color. HD 189733b is a gas giant slightly larger than Jupiter, orbiting a star very similar to our Sun. It was discovered in 2005 by a team of French astronomers using the radial velocity method. They detected the gravitational wobble of the parent star and calculated the planet's mass at 1.138 times Jupiter's mass. The radius measures 1.138 times Jupiter's radius, nearly identical proportions. But the similarity ends there. HD 189733b orbits its star at a distance of 0.031 astronomical units. For context, Mercury, the closest planet to our Sun, orbits at 0.39 astronomical units. This exoplanet orbits 12 times closer than Mercury. The orbital period is 2.219 days, less than 53 hours. The planet screams around its star at speeds exceeding 150,000 miles per hour. At this distance, the stellar radiation is ferocious. The planet's dayside reaches temperatures of 1,700 degrees Fahrenheit. Hot enough to melt glass, hot enough to vaporize silicate compounds that exist as solid minerals on Earth, and that is exactly what happens. In 2008, astronomers using the Hubble Space Telescope pointed its spectrograph at HD 189733b during a transit. They were not photographing the planet. They were analyzing the starlight filtering through its atmosphere. When light passes through a gas, specific wavelengths get absorbed depending on what chemicals are present. Each molecule has a spectral fingerprint. By measuring which wavelengths are missing, scientists can determine atmospheric composition. The results were unprecedented. The atmosphere contains silicon compounds, magnesium silicate particles. On Earth, we call this material orthopyroxene. It forms igneous rocks. Basalt contains it. The planet's atmosphere contains vaporized rock, but the atmospheric conditions are not uniform. HD 189733b is tidally locked. The same hemisphere always faces the star. The day side remains in perpetual blazing light. The night side remains in perpetual frozen darkness. This creates a permanent temperature gradient of over 1,000 degrees between the two hemispheres. Heat does not distribute evenly. The atmosphere tries to reach equilibrium. Hot air on the day side rises and flows toward the cooler night side. Cold air on the night side sinks and flows back toward the day side. This creates a global circulation pattern, a thermal engine powered by the star's relentless radiation, and the wind speed is apocalyptic. In 2014, a team led by astronomers at the University of Warwick used Doppler spectroscopy to measure the wind velocity on HD 189733b. They detected winds moving at 5,400 miles per hour, 7 times faster than the speed of sound on Earth, 2.4 kilometers per second. To put this in perspective, the fastest winds ever recorded on Earth were 318 miles per hour during Tropical Cyclone Olivia in 1996. The jet stream at cruising altitude moves at around 120 miles per hour. A Category 5 hurricane sustains winds of 157 miles per hour or greater. HD 189733b has winds 34 times faster than a Category 5 hurricane. These are not gusts. These are sustained global atmospheric flows that never stop. Ever. The wind speed creates conditions that do not exist anywhere in our solar system. Jupiter has the fastest winds among our planets, reaching speeds of 400 miles per hour in its jet streams. Saturn's winds hit 1,100 miles per hour near its equator. These are violent by terrestrial standards, but they are gentle breezes compared to HD 189733b. At 5,400 miles per hour, atmospheric particles achieve destructive kinetic energies. Objects moving at hypersonic velocities do not push you. They penetrate you. They shred you at the molecular level. But on HD 189733b, the deadly projectiles are not simple gas molecules. They are glass. Here is how it works. On the day side, temperatures exceed 1,700 degrees Fahrenheit. Silicate minerals vaporize into gas. The atmospheric circulation carries this vaporized silicon toward the night side. As the gas crosses into the cooler regions, the temperature drops below the condensation point. The silicon vapor crystallizes. It forms tiny solid particles, droplets of molten glass that cool and harden as they fall. But they do not fall straight down, they fall sideways. The 5,400 mile-per-hour winds carry the glass particles horizontally across the planet. They rain sideways through the atmosphere, driven by hypersonic winds, slamming into anything in their path. This is not a metaphor. The planet literally has storms, where glass shards blow sideways at speeds that would vaporize any spacecraft humanity has ever built. The composition of the glass rain is magnesium silicate, similar to the olivine and pyroxene minerals found in Earth's mantle. On our planet, these minerals exist as solid crystals deep underground. They form through slow cooling of magma over millions of years. They are stable, inert. On HD 189733b, these same minerals exist as atmospheric aerosols, tiny particles suspended in gas circulating endlessly in hurricane-force winds. The particles reflect blue light, which is why the planet appears cobalt blue. The scattering mechanism is similar to why Earth's sky is blue, but the particles doing the scattering are not nitrogen molecules. They are microscopic shards of glass. Frederick Pont, one of the astronomers who confirmed the planet's blue color, stated in 2013 that the glass rain phenomenon was unprecedented. The color comes from silicate particles in a turbulent, hazy atmosphere. The haze is not water vapor, it is pulverized rock. The temperature gradient drives the wind. The wind transports the vaporized silicates. The silicates condense into glass. The glass rains sideways forever. It is a self-sustaining cycle powered by the star's energy. The system will not stop as long as the star shines, and the star will shine for billions of years. The tidal locking adds another layer of horror. One side of the planet bakes under constant radiation. The other side freezes in eternal night. If you stood on the surface, assuming the planet has a surface beneath its thick atmosphere, you would experience two completely different environments depending on your location. On the day side, the star hangs motionless in the sky. It never sets. It never moves. The radiation is so intense that any exposed surface heats to melting temperatures within minutes. The sky glows white with scattered light. The horizon blurs into a shimmering haze. There is no relief, no night, no cooling period, just endless heat. On the night side, the star never rises. Darkness is absolute except for the faint glow of distant stars. The temperature drops below -100 degrees Fahrenheit in some models. The cold is not the gentle cold of an Earth winter. It is the deep cold of thermal equilibrium with empty space. Molecules slow down, chemical reactions stop. Anything biological would freeze solid in seconds. The terminator, the boundary between day and night, is a zone of perpetual twilight, a narrow band where the temperature gradient is steepest. This is where the winds reach their maximum velocity. This is where the atmosphere screams as it tries to equalize the impossible temperature difference. If you somehow survived in the terminator zone, protected inside an indestructible observation vessel, you would witness a landscape of constant violence. The sky would be a churning mass of blue haze. Glass particles would stream past your viewport horizontally, moving faster than rifle bullets. The wind would produce a shriek at frequencies beyond human hearing, a mechanical roar created by turbulence on a planetary scale. The magnetic field of HD 189733b is another source of danger. In 2015, observations using X-ray telescopes detected evidence of a strong magnetic field. The planet's rapid rotation, even though it is tidally locked to its star, maintains a dynamo effect in its interior. Electrically conductive fluids swirl in the planet's core, generating magnetic fields. But unlike Earth's protective magnetic field, which shields us from solar wind, this planet's field interacts with the intense stellar radiation in destructive ways. The magnetic field lines get twisted and tangled by the supersonic atmospheric flows. Magnetic reconnection events release bursts of X-rays and particle radiation. The space around the planet is a soup of high-energy particles. Any spacecraft approaching HD 189733b would need shielding beyond current technology. The radiation environment is lethal. Electronics would fail. Biological tissue would suffer catastrophic DNA damage within hours. There is no safe orbit, no safe landing zone. The planet is hostile at every altitude. The discovery of HD 189733b fundamentally changed how astronomers think about exoplanet atmospheres. Before this planet, scientists assumed that gas giant atmospheres would be relatively simple. Hydrogen, helium, maybe some methane and ammonia. The familiar chemistry of Jupiter and Saturn. But hot Jupiters operate under different rules. The extreme temperatures drive exotic chemistry. Molecules that are stable at room temperature break apart. Elements that normally form solid minerals vaporize. The atmosphere becomes a high-temperature chemical reactor producing compounds that do not exist on Earth outside of laboratories. The presence of vaporized silicates proves that hot Jupiters can have geological atmospheres. The distinction between atmosphere and crust blurs. Minerals that belong underground are floating in the sky. Weather patterns include phenomena that sound like fantasy, but are thermodynamically inevitable given the conditions. Scientists have detected similar atmospheric compositions on other hot Jupiters. WASP-17b, another exoplanet, shows evidence of aluminum oxide in its atmosphere. Corundum. On Earth, we call it sapphire when it is blue and ruby when it is red. On WASP-17b, it exists as vapor. The planet has clouds made of vaporized gems. HAT P7b has atmospheric flows carrying aluminum oxide and titanium oxide. The condensation of these compounds creates clouds that glitter in reflected starlight. But the beauty is entirely lethal. HD 189733b set the template for understanding these extreme atmospheric systems. It was the first exoplanet where astronomers directly detected atmospheric winds through Doppler measurements. It was the first where the true color was determined with certainty. It was the first where the concept of glass rain moved from theoretical possibility to confirmed reality. The technique used to measure the wind speed was elegant. As the planet transits its star, light passes through the planet's atmosphere at the edges. The motion of the atmosphere causes Doppler shifts in the spectral lines. Gas moving toward Earth shifts the lines toward blue wavelengths. Gas moving away shifts them toward red. By measuring these shifts, astronomers calculated the velocity of atmospheric flows. The wind speed of 5,400 miles per hour is not a peak value during a storm. It is the average persistent velocity of the global circulation. This means the entire atmosphere is in a state of permanent hurricane force motion. There are no calm periods. No breaks. The weather never improves. The kinetic energy contained in these winds is staggering. The mass of the atmosphere, multiplied by the square of the velocity, gives energy values comparable to nuclear weapons detonating continuously across the entire planet. The energy source is the star. As long as radiation hits the day side, the thermal engine continues running. Climate models of HD 189733b show complex three-dimensional flow patterns. The simplest models predict a single equatorial jet stream carrying heat from day to night. More sophisticated simulations reveal multiple jet streams at different latitudes and altitudes. Vortices form and dissipate. Turbulence cascades from large scales to small scales. The atmosphere is dynamically unstable, always churning, never reaching equilibrium. The glass rain falls not as isolated droplets, but as dense curtains of particles. Concentrations vary with altitude and latitude. Near the terminator, where the temperature gradients are steepest, the particle density reaches maximum values. The air becomes opaque with suspended silicates. Visibility drops to zero. Flying through this region would be like flying through a sandblaster operating at Mach 7. The impact velocity of individual glass particles renders them deadly. On Earth, hailstones falling at terminal velocity of around 100 miles per hour can dent cars and injure people. Glass particles moving at 5,400 miles per hour carry kinetic energy 54 times greater. They would not bounce off a surface. They would penetrate like bullets. They would ablate material. They would erode any exposed structure. The surface of HD 189733b, if it has a solid or liquid surface beneath the atmosphere, would be under constant bombardment. Any rocky core or liquid metallic hydrogen ocean would experience perpetual impacts from falling glass. Over millions of years, this produces erosion on a scale impossible on Earth. But the planet's nature as a gas giant means it likely has no solid surface. The atmosphere transitions gradually into denser and denser layers as you descend. The pressure increases exponentially. Temperature increases with depth. Eventually, hydrogen gas becomes so compressed that it transitions into a liquid. Deeper still, it becomes metallic. Electrons separate from protons. This substance conducts electricity like metal even though it is made of hydrogen. So if you fell through the atmosphere of HD 189733b, you would experience increasing heat, increasing pressure, and glass particles shredding your descent vehicle. You would pass through zones of different chemistry as temperature and pressure change the equilibrium states of molecules. Eventually, pressure would crush your vessel. Long before you reached any core, you would be compressed into a sphere of plasma and debris. The danger of HD 189733b is multifaceted. It is thermal danger, radiological danger, kinetic danger, chemical danger, pressure danger. Every environmental parameter is hostile. There is no safe zone, no refuge, no habitat module we could build would survive more than seconds on this world. And yet, in the cosmic catalog of exoplanets, HD 189733b is not even the most extreme. It is merely the first where we confirmed the glass rain phenomenon. It is the prototype, the proof of concept that planets can weaponize their own atmospheres. Dozens of similar worlds exist in our detection catalog, each one slightly different, each one pushing a different physical parameter to its limit. Some have faster winds, some have higher temperatures, some orbit even closer to their stars. HD 189733b teaches us that planetary environments exist on a spectrum far wider than we imagined. Earth sits at one end, comfortable, stable, forgiving. This blue gas giant sits at the opposite end, violent, chaotic, merciless. The pale blue dot that inspired hope in 2013 is, in reality, a blue sphere of airborne glass. Moving at hypersonic speed through perpetual darkness and perpetual light. It is beautiful the way a nuclear explosion is beautiful. The aesthetics are undeniable. The danger is absolute. There are stars in the universe cooler than Celt 9b. This is not hyperbole. This is measured fact. Red dwarf stars, the most common stellar type in the galaxy, burn at surface temperatures between 3,000 and 4,000 degrees Fahrenheit. Celt 9b reaches dayside temperatures exceeding 8,000 degrees Fahrenheit. This planet is hotter than 30% of all stars in the Milky Way. It should not exist. And in cosmic terms, it will not exist for much longer. Celt 9b orbits a star designated Celt 9, located approximately 670 light-years from Earth, in the constellation Cygnus. The star itself is unusual. An A-type star, burning at temperatures near 10,000 degrees Fahrenheit, it is one of the hottest stars known to host planets. Most exoplanets orbit cooler, sun-like G-type stars or even cooler red dwarfs. Finding planets around hot, massive stars is rare because these stars live fast and die young, often before stable planetary systems can fully form. The planet was discovered in 2017 by the Kilodegree Extremely Little Telescope Survey, a project using small robotic telescopes to scan the sky for transiting exoplanets. The acronym KELT sounds almost casual, but the discovery it made revealed a world operating at the absolute edge of planetary physics. KELT 9b is a gas giant with approximately 3 times the mass of Jupiter, but less than half the volume. This means it is dense, compressed. The intense stellar radiation heats the planet so severely that the atmosphere puffs up and expands, but gravity pulls it back down. The result is a planet that is simultaneously inflated by heat and crushed by gravity, locked in a battle between expansion and collapse. The orbital period is 1.48 days, 36 hours. The planet orbits at just 0.034 astronomical units from its star, closer than HD 189733b orbits its sun. But KELT 9 is a far more violent star. It pumps out radiation at wavelengths and intensities that would sterilize Earth in hours. The dayside temperature reaches 7,800 degrees Fahrenheit according to measurements published in Nature in 2017. Some models push the estimate as high as 8,600 degrees. At these temperatures, molecules cannot exist. They break apart into individual atoms. Water, methane, ammonia, all the familiar molecules of planetary atmospheres dissociate instantly. Even molecular hydrogen, the most stable molecule in the universe, splits into atomic hydrogen. The atmosphere of KELT 9b is not made of compounds. It is made of atoms, hydrogen atoms, helium atoms, iron atoms, magnesium atoms, titanium atoms. The periodic table exists in the sky as a diffuse gas of disconnected elements. In 2018, astronomers using high-resolution spectroscopy detected iron and titanium in the planet's atmosphere. On Earth, iron is a solid metal that melts at 2,800 degrees. Titanium melts at 3,000 degrees. On KELT 9b, these metals exist as vapor. The atmosphere contains vaporized heavy metals swirling at temperatures hot enough to destroy any known material. The detection was made using the HARPS North spectrograph at the Telescopio Nazionale Galileo in the Canary Islands. The team analyzed the light passing through the planet's atmosphere during transit and identified the spectral absorption lines of neutral iron and singly ionized titanium. These elements absorb specific wavelengths of light, creating a fingerprint that confirms their presence. But iron and titanium are just the beginning. Follow-up observations detected sodium, magnesium, chromium, and other heavy elements. The entire upper atmosphere is a metallic vapor. If you could stand on this planet and look up, the sky would not be blue or black. It would shimmer with a metallic haze glowing dull red from thermal emission. The temperature is so high that atoms themselves are ionized. Electrons are stripped away by thermal collisions and ultraviolet radiation. The atmosphere becomes a plasma, a fourth state of matter. But where electrons move independently of nuclei, plasma conducts electricity. It responds to magnetic fields. The atmosphere is no longer neutral gas. It is an ionized soup that behaves more like the outer layers of a star than a planetary atmosphere. This creates a phenomenon called atmospheric escape. The energy pouring into the atmosphere is so intense that atoms achieve escape velocity and stream away into space. The planet is evaporating. Astronomers detected an extended envelope of escaping gas around KELT 9b that stretches millions of miles into space, forming a comet-like tail as the planet plows through the stellar wind. The mass loss rate is staggering. Current estimates suggest KELT-9b loses approximately 10,000 to 100,000 kilograms of atmosphere every second. That is 10 to 100 metric tons per second. Per day, the planet loses between 860 million and 8.6 billion kilograms of mass. It sounds catastrophic, but given the planet's total mass of approximately 5.8 times 10 to the power of 27 kilograms. Atmospheric escape at this rate would take trillions of years to evaporate the entire planet, but KELT 9b does not have trillions of years. The star itself will expand into a red giant in approximately 300 million years. When that happens, it will engulf the planet completely. KELT 9b is doomed not by atmospheric escape, but by stellar evolution. It will be swallowed. The planet is tidally locked, meaning the same side always faces the star. The day side is a furnace. The night side, by contrast, is relatively cool at around 3,000 degrees Fahrenheit. Cool is a relative term. 3,000 degrees is still hot enough to vaporize most metals, but compared to the 8,000-degree day side, it is practically frigid. This temperature gradient drives atmospheric circulation similar to HD 189733b, but at even higher velocities. Computer models predict wind speeds potentially exceeding 6,000 miles per hour. The winds carry vaporized metals from the day side to the night side. As the vapor cools, the metals condense into tiny solid particles. Clouds form. But these are not water clouds. They are clouds of iron dust, titanium dust, magnesium dust. On the night side, it rains metal. Iron droplets fall through the atmosphere, only to vaporize again as they are swept back toward the day side by returning circulation currents. The entire planet is locked in a cycle of vaporization and condensation. The weather forecast for KEAEAEA reads like an industrial accident. Heavy iron rain on the night side. Vaporized metal fog on the day side. Hypersonic metal-laden winds in the terminator zones. No clearing expected, ever. The radiation environment is lethal beyond comprehension. Kilt 9 is an A-type star pumping out enormous amounts of ultraviolet radiation. At the planet's orbital distance, the UV flux is millions of times higher than what Earth receives from the Sun. Ultraviolet light ionizes atoms and breaks chemical bonds. It destroys organic molecules. DNA would shred instantly. Proteins would denature. Any biological material would be sterilized in microseconds. But UV is not the only threat. The star also emits X-rays and extreme ultraviolet radiation. These high-energy photons penetrate deep into the atmosphere, ionizing gas layers and creating complex plasma physics. The interaction between the stellar wind and the planet's escaping atmosphere generates shock waves and magnetic turbulence. Kilt 9b has no magnetic field of its own that we have detected. The intense heat and rapid rotation may disrupt any dynamo effect in the planet's interior. Without a magnetic field, the planet is defenseless against the stellar wind. Charged particles from the star slam directly into the upper atmosphere, accelerating atmospheric escape and heating the gas to even higher temperatures. The planet's size is paradoxical. Despite being 3 times more massive than Jupiter, it is much smaller in volume. Jupiter has a radius of approximately 44,000 miles. Kilt 9b has a radius of only about 52,000 miles, despite triple the mass. The difference is density. The planet is compressed. The compression comes from 2 sources. First, the planet's high mass generates strong gravity that squeezes the interior. Second, the intense heating from the star causes the atmosphere to expand, but the core remains compressed. The result is a planet with a bloated atmosphere and a dense core, creating an unusual structure that challenges models of planetary interiors. Scientists debate what the interior of Kilt 9b looks like. At the center, pressures exceed millions of atmospheres. Hydrogen transitions into metallic hydrogen, a state where the element behaves like liquid metal, conducting electricity and generating heat through compression. Deeper still, there may be a rocky or icy core containing heavier elements left over from the planet's formation. But accessing the interior is impossible. The atmospheric pressure increases exponentially with depth. At a depth of just a few hundred miles, the pressure reaches levels that would crush any probe humanity could build. Diamond, the hardest natural substance on Earth, would be compressed into a denser carbon phase. Steel would flow like water under the stress. The most disturbing aspect of Kilt 9b is its future trajectory. Orbital models show that the planet is on a death spiral. Tidal interactions with the star are causing the orbit to decay. The planet is moving closer to the star year by year, century by century. The orbital period is shortening. Eventually, in a few million years, the planet will cross the Roche limit, the distance at which tidal forces overcome the planet's self-gravity. When that happens, Kilt 9b will be torn apart. The side facing the star will be pulled more strongly than the far side. The difference in gravitational force will stretch the planet into an elongated ellipsoid. As it crosses the Roche limit, the planet will disintegrate. Material will stream away from the planet in all directions, forming a ring of debris around the star. Some material will fall into the star. Some will be blown away by stellar wind. None will remain in planetary form. This is not speculation. We have observed the Roche limit in action elsewhere. Saturn's rings are the remnants of a moon, or moons that crossed too close and were shredded by tidal forces. Comet Shoemaker-Levy 9 was torn apart by Jupiter's gravity in 1992 and crashed into the planet in 1994. The physics is well understood. The outcome is certain. Kilt 9b is a planet dying in real time. Every observation we make captures it in a state closer to disintegration. Astronomers are essentially watching an execution in slow motion. The sentence was passed millions of years ago when the planet's orbit first began to decay. The execution will be completed millions of years in the future when the planet crosses the Roche limit. But the process is already underway. The discovery of Kilt 9b forced astronomers to revise upper temperature limits for planetary atmospheres. Before this planet, scientists assumed that planets above 5,000 degrees would lose their atmospheres so rapidly they could not persist. Kilt 9b proves that planets can survive at much higher temperatures, at least temporarily. The key word is temporarily. The planet is evaporating. It will not last forever. But for now, it exists, and it expands our understanding of what conditions planets can endure. The planet also challenges theories of planet migration. Hot Jupiters like Kilt 9b did not form where they currently orbit. Gas giants require enormous amounts of hydrogen and helium, which only exist in abundance in the cold outer regions of protoplanetary disks. These planets form far from their stars, beyond the snow line where water ice is stable. Something caused Kilt 9b to migrate inward. Gravitational interactions with other planets in the system may have scattered it into an eccentric orbit that brought it close to the star. Tidal interactions with the star then circularized the orbit, leaving the planet in its current death trap. Alternatively, the planet may have migrated inward through interactions with the protoplanetary disk itself, spiraling slowly toward the star as drag forces sapped its orbital energy. Either way, the migration was a catastrophe for the planet. It moved from a safe, stable orbit in the cold outer system to a hellish orbit in the inner fire. And now it pays the price. Its atmosphere is boiling away. Its orbit is decaying. Its future is annihilation. If you could somehow build a probe capable of withstanding the heat, radiation, and pressure, and sent it to orbit Kilt 9b, what would it observe? The view would be dominated by the star. Kilt 9 is a massive, hot star that would fill a large portion of the sky. It would not appear as a disk, like our Sun. It would be a blazing hemisphere of light, too bright to look at directly, radiating heat that you could feel pressing against the probe like a physical force. The planet itself would glow. The day side would emit thermal radiation in the visible spectrum. It would shine dull red or orange from its own heat, like a piece of metal in a furnace. The night side would be darker, but still glowing faintly. Clouds of condensing metal would drift across the terminator, catching the starlight and sparkling briefly before vaporizing again as they rotated into daylight. The escaping atmosphere would be visible as a faint halo around the planet, streaming away into space like smoke from a fire. The stellar wind would buffet this escaping gas, creating bow shocks and turbulence visible in ultraviolet wavelengths. The entire system would be a chaotic maelstrom of heat, light, and magnetic fields. No human will ever visit Kilt 9b. No robot we build could survive there. The planet exists as a data point, a collection of spectral lines and transit light curves. A mathematical model validated by observation, but forever beyond physical reach. And that is the nature of dangerous planets. They exist. They orbit real stars. They follow the laws of physics. But they are fundamentally inaccessible. They are objects of study, not destinations. They teach us about the universe not through exploration, but through remote observation and theoretical modeling. Kilt 9b is the hottest exoplanet ever discovered. It holds the record. But records are meant to be broken. Somewhere in the galaxy, there may be planets orbiting even hotter stars, planets with even more extreme temperatures. planets pushing even closer to the absolute physical limits of what planetary matter can endure. We have not found them yet, but the universe is vast, and our search is just beginning. "490 light-years from Earth, a planet is committing suicide. It is not dying from external forces. It is not being destroyed by its star or torn apart by tidal stress. It is destroying itself from within." Chronicles 7b is a world where the distinction between solid surface and atmosphere has collapsed entirely. The crust is boiling. The atmosphere is made of vaporized rock. And every day, millions of tons of the planet's own body escape into space, never to return. This is the first rocky exoplanet ever discovered, the first world outside our solar system confirmed to have a solid surface. Astronomers celebrated the discovery in 2009. They thought they had found Earth's distant cousin. They had not. They had found Earth's nightmare. Chronicles 7b was discovered by the French space agency's Chronicles telescope, the Convection Rotation and Planetary Transits mission, launched in 2006. The telescope monitored over 160,000 stars, searching for the telltale dimming that signals a planetary transit. In February 2009, astronomers announced the detection of a super-Earth orbiting the star Chronicles 7. Super-Earth is a misleading term. It suggests a planet similar to Earth but larger, a scaled-up version of home. The reality is far more alien. Chronicles 7b has approximately 8 times Earth's mass and is 60% larger in diameter. But the similarities end there. The planet orbits at 0.017 astronomical units from its star. Mercury orbits our Sun at 0.39 astronomical units. Venus orbits at 0.72. Earth orbits at 1.0. Chronicles 7b orbits 23 times closer than Mercury, 59 times closer than Earth. The orbital period is 0.854 days, 20.5 hours. The planet screams around its star in less than 1 Earth day. At this distance, the stellar radiation is apocalyptic. The dayside temperature exceeds 4,000 degrees Fahrenheit. The surface glows red-hot from thermal emission. Any spacecraft approaching the planet would detect it not by reflected sunlight, but by its own thermal glow. It shines like a lump of metal in a blast furnace. But Chronicles 7b is not made of metal. It is made of rock, silicate minerals, iron and magnesium compounds, the same materials that form Earth's crust and mantle. Except on this planet, those materials exist in states that do not occur naturally on Earth. At 4,000 degrees, rock does not remain solid. It melts, it vaporizes. The surface is an ocean of liquid magma covering the entire dayside. The ocean is not water, it is molten stone. Basalt lava flows covering every square meter of the hemisphere facing the star. The temperature is uniform because the lava circulates, convecting heat from below and radiating it into space from above. The lava ocean has waves, not from wind, because there is no atmosphere in the traditional sense. The waves are tidal waves generated by the star's gravity. The star raises tides in the magma ocean, just as the moon raises tides in Earth's oceans. But these tides are massive. The gravitational gradient across the planet is steep enough to pull the magma into bulges. The ocean rises toward the star and away from it, creating a permanent pattern of deformation. As the planet rotates, material flows through these tidal bulges. The lava cycles continuously. Fresh magma rises from the interior. Heated by gravitational compression and radioactive decay, the magma spreads across the surface, cooling slightly as it radiates heat into space. Eventually, it sinks back down, displaced by newer, hotter material welling up from below. This convection cycle operates on timescales of hours or days. The entire surface is renewed constantly. There are no ancient features, no craters, no mountains, no geological history preserved in stone. The surface is erased and rewritten every planetary day. But the lava ocean is not even the most extreme feature. The atmosphere is worse. In 2012, astronomers using computer models calculated what kind of atmosphere a rocky planet at Chronicles 7b's orbital distance would develop. The answer was unprecedented. The atmosphere would be composed of vaporized rock, sodium vapor, silicon monoxide vapor, potassium vapor, magnesium vapor, oxygen molecules freed from silicate minerals. Follow-up observations confirmed the predictions. Spectroscopy detected sodium in the planet's atmosphere, vaporized from the surface by the intense heat. The detection proved that the surface was hot enough to vaporize minerals directly into gas. This creates an atmospheric cycle, unlike anything in our solar system. On the day side, rock vaporizes from the magma ocean. The vapor rises into the thin atmosphere, forming a haze of mineral gas. Atmospheric circulation carries the vapor toward the cooler night side. As the temperature drops, the vapor condenses. It rains. But the rain is not water. It is liquid rock. Droplets of molten silicate fall from the sky onto the night side surface. The night side is tidally locked into permanent darkness. The temperature drops to around 2,000 degrees Fahrenheit, still hot enough to melt lead, still hot enough to vaporize most organic compounds, but cool compared to the day side. The temperature difference is enough to cause phase transitions. The rain of molten rock accumulates on the night side. It pools into lakes and seas of lava, still glowing dull red from residual heat. The lava cools further, solidifying into igneous rock. Basalt plains form, temporary land masses that last until atmospheric circulation transports them back toward the day side. Here is where the cycle completes. Winds, driven by the temperature gradient, blow across the surface at potentially thousands of miles per hour. The winds carry heat. They also carry solid material, dust particles, fragments of rock. The night side crust is eroded by abrasion, broken down into particles small enough to be transported. As the material is carried back toward the day side, the temperature increases. The solid rock heats up, it softens, it melts, it vaporizes. The cycle begins again. Solid rock on the night side becomes liquid lava on the terminator becomes vapor on the day side. The planet is a distillation column operating on a global scale. The atmospheric composition is toxic and corrosive. Silicon monoxide reacts with oxygen to form silicon dioxide, which we know as quartz on Earth. But at these temperatures, quartz exists as gas. Breathing this atmosphere, if breathing were somehow possible, would be like inhaling powdered glass mixed with superheated steam. The vapor would condense in your lungs. Quartz crystals would form in your alveoli. You would suffocate on gemstones growing in your respiratory system. The pressure at the surface is estimated at only a few millibars, similar to the atmospheric pressure on Mars. This is far lower than Earth's 1,000 millibar surface pressure. The atmosphere is thin because the planet's gravity, while stronger than Earth's, cannot hold onto vaporized rock molecules moving at high thermal velocities. And this brings us to the most disturbing feature of Chronicles 7b. The planet is evaporating. Atmospheric escape is the process by which a planet loses its atmosphere to space. It happens when gas molecules achieve velocities exceeding the escape velocity. On Earth, escape velocity at the surface is about 7 miles per second. Hydrogen molecules in Earth's upper atmosphere occasionally reach this speed. Through thermal motion and solar radiation, which is why Earth has lost most of its primordial hydrogen over billions of years. On Chronicles 7b, the escape velocity is approximately 16 miles per second due to the planet's higher mass and smaller radius. But the temperature is so high that vaporized rock molecules can reach these speeds. Sodium atoms, silicon atoms, oxygen molecules. They are energized by stellar radiation and thermal collisions until they achieve escape velocity and stream away into space. Current estimates suggest Chronicles 7b loses between 10,000 and 100,000 kilograms of mass per second through atmospheric escape. That is the equivalent of 10 to 100 metric tons per second. Over the course of a year, the planet loses between 300 million and 3 billion metric tons of material. This sounds catastrophic until you calculate the total mass. Chronicles 7b has a mass of approximately 8 Earth masses, which equals 4.8 times 10 to the power of 25 kilograms. At the current loss rate, it would take trillions of years to evaporate completely. The planet will die long before that. But the mass loss has consequences. The escaping material forms an extended envelope around the planet, similar to the exosphere observed around Mercury. Sodium atoms, particularly abundant in the escaping gas, scatter sunlight strongly. Observations have detected this sodium cloud extending millions of miles from the planet, forming a faint tail that streams away from the star like a comet's tail. The mechanism driving atmospheric escape is called thermal evaporation. Stellar radiation heats the upper atmosphere to temperatures exceeding 10,000 degrees. At this temperature, atoms move fast enough to overcome gravity. Ultraviolet photons from the star also ionize atoms, stripping away electrons and creating charged particles that respond to magnetic fields and stellar wind pressure. These charged particles are swept away from the planet by the stellar wind, carrying neutral atoms along with them. The planet has no significant magnetic field to protect it. Unlike Earth, whose magnetic field deflects solar wind and prevents atmospheric stripping, Chronicles 7b is defenseless. The stellar wind impacts the upper atmosphere directly, eroding it continuously. The interior structure of Chronicles 7b is a subject of ongoing research. The planet's density is approximately 5.6 grams per cc, slightly higher than Earth's 5.5. This suggests a rocky composition with an iron core making up approximately 30 to 50% of the planet's mass. But the extreme surface conditions affect the interior in ways that do not occur on Earth. The immense heat conducted downward from the surface raises internal temperatures far above normal levels. The mantle, the layer between the crust and core, is likely entirely molten. Convection currents in the mantle transport heat from the core to the surface, feeding the lava ocean above. The core itself may be partially molten. On Earth, the outer core is liquid iron and nickel, while the inner core is solid due to pressure overcoming the melting temperature. On Chronicles 7b, the higher temperatures may keep the entire core molten, eliminating any solid inner core. This would affect the planet's moment of inertia and potentially prevent the generation of a strong magnetic field through dynamo action. Tidal heating adds additional energy to the interior. The planet's orbit is likely slightly eccentric, meaning the distance from the star varies over each orbit. This variation causes the star's gravitational pull to fluctuate, flexing the planet's interior. The friction generated by this flexing produces heat, similar to how bending a paperclip back and forth makes it hot. On Chronicles 7b, tidal heating may contribute significant energy to the interior, maintaining the molten state of the mantle and preventing the surface from solidifying even on the night side. The planet's formation history is puzzling. Rocky planets typically form in the inner regions of protoplanetary disks, where temperatures are high enough to condense silicate minerals, but too high for volatile compounds like water to freeze. Chronicles 7b likely formed closer to its current location than hot Jupiters, which migrate inward from distant orbits. But models suggest the planet may have originally been much larger. It may have started as a Neptune-like world with a thick hydrogen and helium atmosphere. Over billions of years, the intense stellar radiation stripped away the light gases, leaving behind only the rocky core. This process, called photoevaporation, can remove enormous amounts of atmospheric mass, transforming a gas giant into a bare, rocky core. If this scenario is correct, Chronicles 7b is the leftover core of a gas giant. The planet we observe today is a remnant, a ghost of a larger world that once existed. The current mass loss through atmospheric escape is the final stage of a process that has been ongoing for billions of years. The star Chronicles 7 itself is slightly smaller and cooler than our Sun, a G-type star with a surface temperature of about 9,700 degrees Fahrenheit. It is approximately 1.5 billion years old, relatively young compared to the Sun's 4.6 billion years. The star's youth means it emits higher levels of ultraviolet radiation and X-rays, which accelerate atmospheric escape on the planet. The stellar wind from Chronicles 7 is stronger than the solar wind experienced by Earth. This adds to the stripping effect, continuously blasting away the planet's escaping atmosphere and preventing it from forming a stable, thick envelope. The interaction between the stellar wind and the escaping sodium creates complex plasma physics in the space around the planet. Chronicles 7b represents a class of exoplanets called lava worlds. These are rocky planets orbiting so close to their stars that surface temperatures exceed the melting point of rock. Dozens of lava worlds have been discovered since Chronicles 7b, K2141b, 55 Cancri, Kepler 10b. Each one has slightly different properties, but all share the fundamental characteristic of molten surfaces. These planets challenge our understanding of planetary habitability. The concept of the habitable zone assumes that liquid water is necessary for life. But lava worlds exist far inside the habitable zone, in regions where water cannot exist in any form. If life requires liquid water, lava worlds are categorically uninhabitable. But some scientists speculate about exotic forms of life that might use liquid silicates instead of liquid water as a solvent. Hypothetical silicon-based biochemistry operating at high temperatures. Such life would be fundamentally different from Earth life, using entirely different chemistry. It remains pure speculation with no evidence. But the existence of lava worlds forces us to ask the question. The danger of Chronicles 7b is immediate and absolute. Landing on the surface would be suicide. Any spacecraft touching down on the day side would sink into liquid magma within seconds. The material of the spacecraft hull would melt, mixing with the lava ocean. The internal components would vaporize. Within minutes, no trace of the spacecraft would remain. It would be consumed entirely, broken down into constituent atoms, and dispersed through the lava ocean. Landing on the night side would offer no advantage. The surface temperature of 2,000 degrees is still far above the melting point of aluminum, 1,200 degrees, and steel, 2,500 degrees. Only materials like tungsten, melting point 6,000 degrees, or ceramics could withstand brief exposure. But even these materials would eventually succumb to thermal stress, oxidation, and abrasion from the mineral-laden winds. Orbiting the planet would be safer but still dangerous. The intense heat radiating from the day side would raise the temperature of any spacecraft significantly. Thermal management systems would struggle to dissipate the heat. Solar panels would degrade under the intense ultraviolet radiation from the star. Electronics would fail. Any mission to Chronicles 7b would require technology far beyond our current capabilities. The scientific value of studying Chronicles 7b lies in understanding planetary evolution under extreme conditions. How do rocky planets respond to intense stellar radiation? How fast do they lose mass? What is the final fate of a planet in such an orbit? These questions have implications for understanding planetary system architecture and the long-term stability of rocky worlds. Chronicles 7b also serves as a laboratory for studying high-temperature geochemistry. The phase transitions occurring on the planet's surface happen under conditions impossible to replicate in Earth-based laboratories. The vaporization and condensation of rock minerals, the behavior of liquid silicates at various temperatures and pressures, the formation of exotic mineral phases. All of these processes can be studied remotely through spectroscopy and compared with theoretical models. But perhaps the most important lesson from Chronicles 7b is a sobering one. Rocky planets, even small worlds with solid surfaces, can exist in states utterly hostile to anything recognizable as life. The presence of rock does not guarantee habitability. It does not even guarantee a stable surface. Planets can have oceans. Those oceans can be made of lava. The atmosphere can rain rock. The surface can evaporate into space. The universe creates environments we would not imagine in our darkest nightmares. And those environments are not rare. They are common. They are predictable outcomes of planetary formation around close stellar orbits. Chronicles 7b is not an anomaly. It is a template. Dozens of similar worlds await discovery. Some may be even more extreme. Some may orbit closer. Some may be hotter. Some may have lost more mass. The catalog of lava worlds will grow as our detection methods improve and we survey more stars. And every new discovery will remind us that Earth is not typical. Earth is not even close to typical. Earth is a narrow exception in a universe of extremes. We live on a planet with solid ground, breathable air, and liquid water oceans. These conditions are vanishingly rare when measured against the full diversity of planetary environments. Chronicles 7b forces us to confront the fragility of our existence. We are adapted to one specific set of environmental conditions. Conditions that exist on one planet out of thousands we have discovered. If humans attempted to colonize the galaxy, the vast majority of worlds we encounter would be immediately lethal. The planet is not malevolent. It does not want to kill us. It simply exists in a state where our biochemistry cannot function, where our materials cannot survive, where our presence is impossible. That is the ultimate danger of lava worlds. Not that they would attack us, but that they exist at all. They prove that the universe builds planets under rules that do not consider life, that do not optimize for habitability, that create environments purely as outcomes of gravitational and thermodynamic processes, indifferent to whether those environments can support complexity. Korat 7b is a world dying by evaporation, dissolving into space one atom at a time, screaming in frequencies of sodium emission as its body scatters across the void. It will die slowly, pointlessly, and when it is gone, the universe will not notice. Death has a speed. For WASP-12b, that speed is calculable. The planet loses 6 billion kilograms of mass every second. Not every year, not every day, every single second. In the time it takes you to hear this sentence, WASP-12b has shed 30 billion kilograms of its own body into the void. Astronomers have calculated the exact moment of its destruction. In 10 million years, this planet will cease to exist. It is not dying of old age. It is being consumed, devoured, eaten alive by its own star. WASP-12 is a yellow dwarf star located approximately 870 light-years from Earth in the constellation Auriga. The star itself is unremarkable, slightly larger and hotter than our Sun, burning at about 11,000 degrees Fahrenheit. It has existed for approximately 2 billion years and will continue burning for billions more. But WASP-12 is a predator, and WASP-12b is its prey. The planet was discovered in 2008 by the Super WASP project, the Wide-Angle Search for Planets, using an array of robotic cameras to monitor millions of stars for transits. WASP-12b is a hot Jupiter, a gas giant with approximately 1.4 times Jupiter's mass. But its size is grotesque. The planet's radius is 1.8 times Jupiter's radius, making it bloated and distended. The planet is not spherical. It is egg-shaped, stretched, deformed by forces that are tearing it apart. The orbital period is 1.09 days, 26 hours. The planet orbits at 0.023 astronomical units from its star, roughly 3.4 million miles. For context, the Sun's surface is 430,000 miles in diameter. WASP-12b orbits its star at a distance only 8 times the star's radius. The planet is so close that it skims through the star's outer corona. At this distance, the tidal forces are catastrophic. Tidal force is the difference in gravitational pull between the near side and far side of an object. The Moon creates tides on Earth. The difference in gravitational pull between the side facing the Moon and the side facing away causes ocean water to bulge, creating high tides. The effect is measurable but gentle because the Moon is relatively far away and relatively small. WASP-12b experiences tidal forces billions of times stronger. The side of the planet facing the star is pulled toward the star with far greater force than the far side. The difference is so extreme that the planet is stretched into an ellipsoid. The planet is being pulled apart, slowly, inevitably, and there is nothing that can stop it. In 2009, just 1 year after the planet's discovery, astronomers using the Hubble Space Telescope detected something unprecedented. They observed the planet's atmosphere extending far beyond its nominal radius. The atmosphere was not confined by gravity. It was escaping, streaming away from the planet in a vast comet-like tail that extended millions of miles into space. The tail points away from the star, swept back by the stellar wind and radiation pressure. Material from the planet's atmosphere is being blown into space like smoke from a fire. The escaping gas contains carbon and oxygen, elements liberated from carbon dioxide and carbon monoxide in the atmosphere. The molecules are being torn apart by ultraviolet radiation from the star. The atoms are being ionized and accelerated to high velocities. The mass loss rate is staggering, 6 billion kilograms per second, For comparison, Earth's atmosphere has a total mass of approximately 5 times 10 to the power of 18 kilograms. At WASP-12b's loss rate, the planet would lose the equivalent of Earth's entire atmosphere in approximately 26 years. The planet has been losing mass at this rate for billions of years. It has already lost a significant fraction of its original mass. Scientists calculate that WASP-12b has lost approximately 10% of its total mass since it arrived at its current orbit. The planet may have originally been closer to 2 Jupiter masses. The missing mass has been stripped away and either absorbed by the star or expelled into interstellar space. What remains is a bloated, distended remnant slowly being consumed. But atmospheric escape is only part of the problem. The planet is also experiencing Roche lobe overflow. The Roche lobe is the region around a planet where the planet's gravity dominates. Outside the Roche lobe, the star's gravity is stronger. For a planet in a close orbit, the Roche lobe is teardrop-shaped, with the point facing the star. WASP-12b has expanded so much from stellar heating that it has filled its Roche lobe completely. Material at the planet's surface is no longer gravitationally bound to the planet. It is pulled away by the star's gravity. The planet is overflowing its gravitational boundary like water spilling over the rim of a filled glass. This creates a continuous flow of material from the planet to the star. Gas streams from the planet's atmosphere directly onto the star's surface. The process is called mass transfer, and it occurs in binary star systems, where one star feeds material to its companion. WASP-12b is not a star, but it is massive enough that the same physics applies. The planet is feeding its star, slowly committing suicide by donation. The material flowing from the planet to the star is not random. It follows a specific path determined by gravitational dynamics. The stream forms an arc connecting the planet to the star, following a curved trajectory as it falls inward. When the material reaches the star, it impacts the surface at velocities exceeding 100 miles per second. The kinetic energy of impact heats the gas to millions of degrees, creating a hotspot on the star's surface. Astronomers have detected this hotspot through careful observation. The star's brightness varies slightly depending on where the hotspot is located. When the hotspot faces Earth, the star appears slightly brighter. When it rotates out of view, the brightness decreases. This variation confirms that material from the planet is actively falling onto the star and heating the stellar surface. The temperature on WASP-12b's day side exceeds 4,600 degrees Fahrenheit. This is hot enough to vaporize most metals and break apart most molecules. The atmosphere is a soup of atomic carbon, oxygen, hydrogen, and helium, with trace amounts of heavier elements. Spectroscopic observations have detected carbon monoxide and water vapor. Though the water molecules are short-lived, quickly broken apart by ultraviolet radiation. In 2017, a team of astronomers using the Hubble Space Telescope discovered something even more disturbing. They detected metals in the planet's atmosphere. Not just light elements, but heavy elements: magnesium, iron, titanium. These metals exist as vapor in the planet's upper atmosphere, vaporized from the planet's interior by the extreme heat. The presence of heavy metals suggests that the planet's interior is being exposed. On a normal gas giant like Jupiter, heavy elements are locked deep in the core, separated from the hydrogen and helium envelope by thousands of miles of dense atmosphere. But WASP-12b is losing its envelope. The hydrogen and helium are being stripped away. The core is approaching the surface. Eventually, all that will remain is a barren rocky core, a super-Earth remnant of a once massive gas giant. The planet's interior structure is under immense stress. The tidal forces create enormous internal friction as different parts of the planet are pulled in different directions. This friction generates heat through a process called tidal heating. The same process heats Jupiter's moon Io, making it the most volcanically active body in the solar system. But on WASP-12b, tidal heating operates on a scale millions of times more powerful. The heat generated by tidal friction is so intense that it puffs up the planet's atmosphere to grotesque proportions. The planet has the mass of Jupiter, but the size of a planet twice Jupiter's radius. The density is incredibly low, less than 0.2 grams per cc. For comparison, Jupiter has a density of 1.33 grams per cc. WASP-12b is extraordinarily inflated, held together only by gravity, while being simultaneously torn apart by tidal stress. The planet's orbit is not circular. It is slightly eccentric, with an eccentricity of approximately 0.04. This means the distance from the star varies over each orbit. When the planet is at its closest approach, tidal forces are strongest. When it is farther away, tidal forces weaken slightly. This variation causes the planet to be squeezed and stretched repeatedly every orbit, generating even more tidal heating. The orbit is also decaying. Tidal interactions transfer angular momentum from the planet's orbit to the star's rotation. This causes the orbit to shrink. The planet moves closer to the star. The orbital period decreases. The process accelerates as the planet gets closer because tidal forces increase with decreasing distance. Current models predict that WASP-12b will spiral into its star within 10 million years. This sounds like a long time, but in cosmic terms, it is an eye blink. The planet has existed for approximately 2 billion years. It will be destroyed in half of 1% of its total lifetime. We are observing the planet during its final moments, not its final seconds, but its final geological moment. The death spiral has already begun. When the planet crosses the Roche limit approximately 1.5 million miles from the star, it will disintegrate. Tidal forces will overcome the planet's gravity. The planet will be torn apart into a ring of debris that will quickly fall into the star. The star's brightness will increase slightly as it absorbs the additional mass. Within a few thousand years, no trace of the planet will remain, except for a slight change in the star's composition. The danger of WASP-12b is not that it would kill a visitor. It is that the visitor would arrive at a planet that has already been killed. The planet is a corpse. It is still moving, still orbiting, still radiating heat, but it is already dead. Its fate is sealed. The execution date is set. We are watching a planet on death row. In 2020, astronomers published a study showing that the planet's orbit has detectably decayed over the previous decade. By comparing transit timing measurements from 2008 to 2019, they calculated that the orbital period is decreasing by approximately 29 milliseconds per year. This seems tiny, but it is measurable. It is proof that the planet is spiraling inward in real time. The decay rate allows precise calculation of the planet's remaining lifetime. Extrapolating the current rate of orbital decay forward, the planet will reach the Roche limit in approximately 10 million years. This estimate assumes the decay rate remains constant, which it will not. As the planet moves closer, tidal forces increase and the decay accelerates. The actual remaining lifetime may be shorter, perhaps as little as 3 million years. The discovery of orbital decay in real time was groundbreaking. It was the first direct observational evidence of a hot Jupiter's death spiral. Theoretical models predicted this process for decades, but WASP-12b provided the first empirical confirmation. The planet is not just predicted to die, it is measured to be dying. The star itself is affected by the planet's presence. The planet's gravity raises tides on the star's surface, similar to how the moon raises tides on Earth. But stellar tides are far more powerful because the star is fluid throughout. Plasma flows within the star respond to the planet's gravitational pull, creating bulges that rotate with the planet's orbit. These tidal bulges dissipate energy through friction, heating the star slightly. The heating is not enough to significantly change the star's properties, but it is detectable through precise measurements of stellar oscillations. Asteroseismology, the study of stellar vibrations, reveals that WASP-12 vibrates at specific frequencies influenced by the planet's tidal forcing. The planet's atmosphere is chemically active despite the extreme conditions. Molecules form and break apart continuously. Carbon monoxide forms when carbon and oxygen atoms collide. Ultraviolet photons break the molecules apart. Water forms when hydrogen and oxygen combine. Radiation destroys it immediately. The atmosphere is a constant cycle of chemical reactions operating at extreme temperatures. Titanium oxide and vanadium oxide, detected in the atmosphere through spectroscopy, act as thermal absorbers. These molecules absorb visible and ultraviolet light from the star, converting it to heat. This heats the upper atmosphere to temperatures exceeding the lower atmosphere, creating a temperature inversion. The planet has a stratosphere, a high-altitude layer hotter than the layers below it. This stratosphere traps heat, making the planet even hotter than it would be otherwise. The greenhouse effect on WASP-12b operates through metal oxides rather than carbon dioxide. It is an industrial greenhouse effect, something that would occur in the exhaust of a smelter, not in nature. Except on this planet, it occurs naturally across the entire atmosphere. The night side of WASP-12b is cooler, but still lethally hot. Models predict night side temperatures around 2000 degrees Fahrenheit. The planet is tidally locked, so the same hemisphere always faces the star. But atmospheric circulation transports heat from the day side to the night side. Supersonic winds blow continuously from day to night, carrying thermal energy and preventing the night side from freezing. These winds reach speeds potentially exceeding 4,000 miles per hour. The winds are driven by the temperature difference between day and night, which exceeds 2,000 degrees. The resulting pressure gradient creates hurricane-force flows that circle the planet perpetually. The winds carry vaporized metals, creating metallic clouds on the night side that rain liquid iron and titanium. But even the night side is not safe from the star's influence. The planet's extended atmosphere means that even the night side is partially illuminated by scattered starlight. The star's light refracts through the thick, distended atmosphere, creating a permanent halo of light around the planet. There is no true darkness, no escape from the star's presence. The magnetic field of WASP-12b, if it exists, is under extreme stress. The planet's rapid orbital motion through the star's magnetic field generates powerful electrical currents. These currents heat the planet's ionosphere and accelerate charged particles to high velocities. The interaction creates intense auroras, far more powerful than Earth's northern lights. But these auroras are not beautiful light shows. They are radiation events that blast the upper atmosphere with high-energy particles. The planet's interior is likely stratified into distinct layers. A rocky core containing heavy elements like iron and silicates. A metallic hydrogen layer where pressure is so high that hydrogen behaves like liquid metal. An outer molecular hydrogen envelope, but the boundaries between these layers are blurred by convection and tidal heating. Material circulates between layers, mixing the interior in ways that do not occur on more stable gas giants. The core itself may be dissolving. Some models suggest that the extreme internal temperatures and pressures are causing the rocky core to melt and mix with the surrounding hydrogen. Heavy elements are being dredged up from the core and transported to the atmosphere, which explains the detection of metals in the upper atmosphere. The planet is not just losing its envelope. It is losing its structural integrity entirely. The formation history of WASP-12b is a story of catastrophic migration. The planet did not form at its current location. Gas giants require cold temperatures to accumulate hydrogen and helium efficiently. WASP-12b formed beyond the snow line, the distance from the star where water ice is stable, probably at a distance of several astronomical units. Something caused the planet to migrate inward. Gravitational interactions with other planets in the system may have scattered it into an elliptical orbit. Tidal interactions with the star then circularize the orbit, trapping the planet in its current death spiral. Alternatively, interactions with the protoplanetary disk may have caused the planet to spiral inward during the system's formation, before the disk dissipated. Either way, the migration was the planet's doom. The planet fell from a safe orbit in the outer system into a trap from which there is no escape. And now it dies slowly, feeding its star with its own substance, watching its orbit decay, waiting for the moment when tidal forces finally exceed its structural strength. If intelligent beings existed on a moon orbiting WASP-12b, they would know the exact date of their apocalypse. They would watch the star grow larger in their sky every year. They would measure the orbital period decreasing. They would calculate the remaining time with perfect precision. And they would know that nothing they could do would change the outcome. The planet has no moons that we have detected. The tidal forces would tear apart any satellite that formed. Any moon that once orbited WASP-12b has long since been destroyed, its remnants absorbed into the planet or flung into interstellar space. WASP-12b is a preview of a future that awaits many hot Jupiters. These planets are common in the exoplanet catalog because they are easy to detect, not because they are common in absolute terms. But among the hot Jupiters we have found, many are on similar death spirals. Many are losing mass, many are filling their Roche lobes. Many will be consumed by their stars within tens of millions of years. The planet is not angry, it is not suffering. It has no consciousness, no awareness of its fate. It is simply an object following the laws of physics. Gravity pulls it inward, tidal forces tear it apart, radiation strips away its atmosphere. These are mechanical processes, deterministic and inevitable. But from a human perspective, watching a planet die is horrifying. We live on a planet. We depend on planetary surfaces for our survival. Seeing another world destroyed reminds us of the fragility of all worlds, reminds us that planets are not eternal. They are temporary structures assembled by gravity, maintained by orbital mechanics, and eventually destroyed by the same forces that created them. WASP-12b will not explode. It will not burn. It will simply fall. Piece by piece, atom by atom, it will fall into its star. The process is already underway. 6 billion kilograms per second, 189 trillion kilograms per year. In 10 million years, the planet's mass will be reduced to zero. The star will continue burning as if nothing happened. And perhaps another planet will form from the debris, only to suffer the same fate. This is the danger of WASP-12b. Not that it threatens us, but that it demonstrates the impermanence of planets. That it shows us orbital mechanics is not always stable. That it proves worlds can die. And that when they die slowly, screaming matter into space for millions of years, while the universe watches indifferently. The planet is being eaten alive. And the meal will take 10 million years to finish. "2,300 light-years from Earth, 3 planets orbit a corpse. The star that birthed them is dead, exploded, gone. What remains is a sphere of neutron-degenerate matter 15 miles across, spinning 161 times per second, blasting focused beams of radiation across the galaxy with the precision of a cosmic lighthouse. The star died violently. The planets survived. And now they circle the corpse in eternal silence, bathed in radiation that would sterilize them millions of times over. These are the pulsar planets, the first exoplanets ever discovered, the first worlds confirmed to exist beyond our solar system. And they orbit the most dangerous stellar remnant in the known universe, PSRB 1257+12. The designation is bureaucratic and cold. Assigned by the position in the sky where the pulsar was discovered, PSR stands for pulsar, a portmanteau of pulsating star. B indicates it was discovered before January 1993. The numbers and plus sign denote right ascension and declination coordinates. But behind this sterile designation lies something primordial and terrible. The discovery happened in 1992. Alexander Wolski, a Polish astronomer working at the Arecibo Observatory in Puerto Rico, was conducting a pulsar timing survey. Pulsars are neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep through space like a lighthouse. When the beam points toward Earth, we detect a pulse. The pulses are extraordinarily regular, more precise than atomic clocks. Wolski was measuring the pulse arrival times from PSRB 1257+12 with microsecond precision. He expected the pulses to arrive with perfect regularity. They did not. The arrival times varied. The variations were not random. They followed a pattern, a periodic pattern that repeated with mathematical precision. The pattern indicated that the pulsar was moving. Something was pulling it back and forth. The gravitational influence of orbiting bodies, planets. The wobble in the pulsar's motion was detectable through the Doppler shift in the pulse arrival times. When the pulsar moved toward Earth, the pulses arrived slightly earlier. When it moved away, they arrived slightly later. Wolski detected not one planet, but 3. The first confirmed planetary system beyond our solar system. The first proof that planet formation is not unique to stable living stars. The first demonstration that worlds can form around stellar corpses. The announcement came in January 1992, though the paper was not published until 1993 in the journal Nature. The astronomical community was stunned. Many scientists had predicted that planets around pulsars should not exist. The supernova explosion that creates a pulsar should destroy any pre-existing planets. The radiation environment should prevent new planets from forming. Yet here was irrefutable evidence. 3 planets orbiting a pulsar. The planets were designated PSRB 1257 plus 12 B, C, and D. Later, a 4th planet was tentatively detected and designated A, though its existence remains unconfirmed. Planet B orbits at 0.19 astronomical units from the pulsar. Its mass is approximately 0.02 times Earth's mass, roughly twice the mass of the Moon. The orbital period is 25.34 days. Planet C orbits at 0.36 astronomical units. Its mass is 4.3 times Earth's mass, making it a super-Earth. The orbital period is 66.54 days. Planet D orbits at 0.46 astronomical units. Its mass is 3.9 times Earth's mass, another super-Earth. The orbital period is 98.21 days. The tentative planet A, if it exists, orbits much closer at approximately 0.1 astronomical units with an orbital period of around 25 days. Its mass would be only 0.004 times Earth's mass, smaller than the Moon. These are rocky planets, terrestrial worlds with solid surfaces. They are not gas giants. They orbit in neat, nearly circular paths. They form a miniature planetary system that resembles the inner solar system in architecture. But the central object is not a star. It is something far more deadly. The pulsar itself has a mass approximately 1.4 times the mass of our Sun, but that mass is compressed into a sphere roughly 15 miles in diameter. The density is incomprehensible. A sugar cube-sized chunk of neutron star material would weigh approximately 100 million tons on Earth. The escape velocity at the surface exceeds 100,000 miles per second, 1/3 the speed of light. The pulsar rotates 161 times per second. The surface is moving at approximately 43,000 miles per second, 14% the speed of light. The rotation generates a magnetic field trillions of times stronger than Earth's magnetic field. This magnetic field accelerates charged particles to relativistic velocities, creating beams of radiation that blast outward from the magnetic poles. These beams contain everything: radio waves, visible light, X-rays, gamma rays, high-energy particles moving at 99% the speed of light. The beams sweep through space with each rotation, creating pulses detectable across thousands of light-years. The pulses from PSRB 1257 plus 12 arrive every 6.218 milliseconds with clock-like precision. The 3 planets orbit directly in the path of these beams. Every 6 milliseconds, they are bathed in a blast of radiation equivalent to standing at ground zero of a nuclear explosion. The radiation dose is measured in thousands of sieverts per second. For reference, a dose of 10 sieverts is lethal to humans. These planets receive radiation doses millions of times higher than any environment in our solar system. The surface of these worlds is bombarded continuously by high-energy particles. Gamma rays, X-rays, cosmic rays accelerated to near light speed. The radiation would ionize any atmosphere. It would break apart molecules. It would sterilize the surface to a depth of meters. DNA would be shredded instantly. Organic chemistry would be impossible. Life as we understand it could not exist, could never have existed, will never exist. But the planets do not have atmospheres to ionize. The radiation pressure and stellar wind from the pulsar would strip away any atmosphere within years. The planets are airless rocks, barren spheres of silicate minerals and iron orbiting in a vacuum. The surface is scoured clean by radiation, smoothed by the constant particle bombardment. There are no craters because there are no impactors. Any asteroid or comet that approaches the pulsar is torn apart by tidal forces or vaporized by radiation. The magnetic field of the pulsar extends far beyond the planet's orbits. The planets move through this magnetic field at high velocities, generating enormous electrical currents. The currents flow through the planets' conductive interiors, heating them from within. This magnetic induction creates thermal energy that keeps the planet's cores molten, despite receiving no thermal radiation from a star. The pulsar does not emit heat like a normal star. It emits radiation across the electromagnetic spectrum, but most of that radiation is in the form of high-energy photons and particles that do not thermalize efficiently. The planet's surface temperatures are determined not by stellar heating, but by internal heat from radioactive decay and magnetic induction. Temperatures likely range from a few hundred degrees above absolute zero to near freezing. Depending on internal heat sources, this makes the pulsar planets some of the coldest worlds, despite orbiting an object that was once the core of a star. The darkness is absolute. There is no sunlight, no starlight strong enough to illuminate the surface. The only light comes from the pulsar's beams, flashing 161 times per second, creating a strobe effect that would disorient any observer. The landscape would be revealed in frozen millisecond-long snapshots, alternating between absolute darkness and brief illumination. The formation of these planets is the greatest mystery. Pulsars form through supernova explosions. When a massive star exhausts its nuclear fuel, its core collapses in less than 1 second. The collapse releases gravitational potential energy, equivalent to the total energy output of all stars in the observable universe for several seconds. The explosion blows away the star's outer layers at 10% the speed of light. The shockwave carries enough energy to obliterate any planets that existed before the explosion. Yet the pulsar planets exist. 3 of them, orbiting in stable circular orbits. This suggests they formed after the supernova. But how? The leading theory proposes that the planets formed from a debris disk created by the supernova. When the star exploded, not all material was ejected into space. Some material, particularly from the star's equatorial regions, was flung into orbit around the newly formed neutron star. This material formed a disk, similar to the protoplanetary disks around young stars. The disk contained heavy elements created during the supernova explosion itself: iron, silicon, magnesium, oxygen. These elements condensed into dust grains. The grains collided and stuck together, forming larger particles. The particles grew into planetesimals. The planetesimals collided and merged, forming planets. The entire process took perhaps a few million years, occurring in the aftermath of the most violent explosion the universe can produce. This scenario is called second-generation planet formation. The planets are made from the ashes of the dead star. They are literally born from the corpse of their parent. It is planetary necromancy on a cosmic scale. Alternative theories exist. One suggests the planets are the remnants of a companion star that was shredded by the supernova. The companion's atmosphere was blown away, leaving only the dense core, which fragmented into multiple bodies that reaccreted into planets. Another theory proposes the pulsar captured rogue planets that were wandering through interstellar space, but gravitational capture is extremely unlikely, requiring precise velocities and trajectories that occur rarely. The debris disk scenario is most widely accepted because it explains the circular coplanar orbits. Captured planets would have chaotic, eccentric orbits. Remnant cores of a destroyed companion would likely have been ejected entirely. Only planets formed from a disk naturally develop circular orbits aligned in the same plane. In 1994, astronomers discovered something remarkable. The orbits of planets C and D are gravitationally coupled. They are in a 3:2 orbital resonance. For every 3 orbits planet C completes, planet D completes exactly 2 orbits. This resonance is stable and self-maintaining. It is identical to the resonance between Neptune and Pluto in our solar system. The presence of orbital resonance is strong evidence for in situ formation. Resonances develop when planets form within a disk and migrate through gravitational interactions. The fact that pulsar planets exhibit the same dynamical behavior as solar system planets suggests they form through similar processes. The only difference is the disk formed from a supernova explosion rather than from a collapsing molecular cloud. The discovery of the pulsar planets changed exoplanet science. Before 1992, the existence of planets around other stars was theoretical. Many astronomers believed them likely. Many had searched for them. But none had been confirmed. The pulsar planets were definitive proof planets exist beyond the solar system. Planet formation is a robust process that occurs even in the most extreme environments. But the discovery also highlighted a disturbing truth. Planets do not require living stars. They can form around dead stars. They can exist in environments utterly hostile to life. The universe creates planets not because they are habitats, but because gravitational accretion is an inevitable consequence of matter existing in rotating disks. Planets are byproducts of physics, not products of biological necessity. The pulsar itself is a window into extreme physics. Neutron stars are the densest objects in the universe except for black holes. The matter is compressed to nuclear density. Protons and electrons are forced together, forming neutrons. The neutrons are packed so tightly that they resist further compression through a neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same state. The interior structure of a neutron star is layered. The outer crust is a crystalline lattice of iron nuclei embedded in a sea of electrons. The inner crust contains neutron-rich nuclei and free neutrons. The outer core is a superfluid of neutrons with a small admixture of protons and electrons. The inner core may contain exotic matter states that do not exist anywhere else in the universe. Quark matter, hyperons, strange matter. These phases of matter are purely theoretical, predicted by quantum chromodynamics but never observed directly. The magnetic field is generated by the rotation of charged particles within the neutron star. The field strength at the surface reaches 1 trillion Gauss. Earth's magnetic field is half a Gauss. The Sun's magnetic field is a few Gauss. The pulsar's field is 1 trillion times stronger. This field accelerates particles to relativistic speeds and confines them in the magnetosphere, a complex structure extending thousands of miles from the surface. The beams originate from the magnetic poles, where field lines are open and particles can escape. Electrons and positrons are accelerated along these field lines, creating cascades of secondary particles. The particles emit synchrotron radiation as they spiral in the magnetic field. This radiation spans the entire electromagnetic spectrum from radio waves to gamma rays. The planets are embedded in this magnetosphere. They orbit through regions filled with relativistic particles and intense electromagnetic fields. The interaction between the planets and the magnetosphere creates plasma wakes, trails of ionized material streaming behind each planet. These wakes may be detectable through radio observations, though no confirmed detection has been made yet. The tidal forces experienced by the pulsar planets are relatively mild compared to planets around stars like WASP-12. Neutron stars are compact but not supermassive. The tidal gradient at the planets' orbital distances is manageable. The planets remain structurally intact. But the tidal locking is immediate. All 3 planets present the same face to the pulsar perpetually. One hemisphere is continuously exposed to the radiation beams. The other hemisphere remains in perpetual darkness, except for the brief flashes as the beams sweep across the sky. The orbital stability of the system is remarkable. The planets have orbited for billions of years without significant perturbations. The system is dynamically stable and will remain so for billions more years. The pulsar loses rotational energy slowly through electromagnetic radiation, causing its spin to decrease. Currently, the spin-down rate is approximately 1 microsecond per century. Eventually, in trillions of years, the pulsar will stop rotating entirely, becoming a cold, dead sphere of neutrons. But even then, the planets will continue orbiting, frozen in eternal night. The discovery techniques used for the pulsar planets were revolutionary. Unlike transit or radial velocity methods used for planets around normal stars, pulsar planets are detected through pulsar timing variations. The method is extraordinarily precise. Pulsar timing can detect orbital motions with amplitudes of mere meters per second. This sensitivity allowed detection of planets smaller than Earth, something impossible with 1990s technology for planets around normal stars. The first exoplanet around a Sun-like star, 51 Pegasi b, was not discovered until 1995, 3 years after the pulsar planets. The pulsar planets thus hold the distinction of being the first confirmed exoplanets in history. They are the proof of concept that launched modern exoplanet science. But they are also a warning. They demonstrate that planets can form in the aftermath of stellar death. They show that worlds can exist in radiation environments millions of times more hostile than anything in our solar system. They prove that the universe creates planetary systems without regard for habitability. If humans ever develop the technology to visit PSRB 1257+12, the mission would be suicide. No shielding could protect against the radiation. The particles are too energetic. The flux is too intense. A spacecraft in orbit would be bombarded by gamma rays and cosmic rays that would destroy electronics and biological tissue within seconds. Any landing would be brief and final. The surface of planet C or D would be alien beyond comprehension. The sky would be black except for the pulsar beams sweeping overhead 161 times per second. The beams would illuminate the landscape in strobe-like flashes, creating disorienting shadows that shift too fast for human eyes to follow. The ground would be bare rock, smoothed by billions of years of radiation bombardment. No dust, no atmosphere, no weather, just rock and darkness and the relentless pulse of radiation. Standing on the surface, you would feel nothing from the radiation. It moves at the speed of light and carries no thermal energy you could sense. But it would be destroying you at the cellular level. DNA molecules would shatter. Proteins would denature. Cell membranes would rupture. You would be dead before your nervous system could register pain. Your body would become radioactive from neutron activation. Your atoms would be transmuted into unstable isotopes. The pulsar planets represent the ultimate hostile environment. They combine the radiation danger of proximity to a neutron star with the isolation of orbiting a dead object. There is no starlight, no thermal energy, no possibility of life. They are monuments to the universe's indifference. Worlds that exist not because they should, but because physics allowed them to form. The discovery that planets can survive supernovae has implications for galactic ecology. Supernovae occur regularly throughout the galaxy. If even a small fraction of them produce planetary systems, there could be millions of pulsar planets in the Milky Way. Most would be undetectable, because their host pulsars do not happen to point beams toward Earth. We may be surrounded by dead worlds orbiting dead stars, invisible to our telescopes, existing in silent darkness. Some scientists speculate about alternative biochemistries that could exist in radiation-rich environments. Hypothetical life forms based on nuclear reactions rather than chemical reactions. Organisms that use neutron fluxes as an energy source instead of sunlight. These ideas remain pure speculation with no supporting evidence. But the pulsar planets force us to consider possibilities beyond Earth-based biochemistry. The pulsar planets also serve as laboratories for testing general relativity under extreme conditions. The intense gravitational field of the neutron star creates space-time curvature that affects the planet's orbits. Measurements of orbital precession and relativistic time dilation can test Einstein's equations in regimes impossible to access in the solar system. So far, all observations match general relativity's predictions perfectly. The 3 planets circling PSRB 1257+12 are among the most dangerous places in the known universe. Not because they would destroy you quickly, though they would, but because they represent something philosophically terrifying. They prove that planetary systems do not require stars, that worlds can exist around corpses, that the universe builds planets in environments where life is impossible by definition. They are warnings written in radiation and gravity. Proof that planet formation is a mechanical process, not a teleological one. The universe does not create planets as homes. It creates them as inevitabilities, as consequences of rotating gas clouds and gravitational accretion. Whether those planets can support life is irrelevant to their formation. The pulsar planets orbit in darkness. They will orbit forever. They are fossils of a catastrophe, remnants of an explosion, worlds born from death. And they teach us that the galaxy is filled with places where the ground is solid, the planets are real, and life is categorically impossible. The lighthouse rotates. The beams sweep through space, the planets orbit in silence, and the corpse at the center pulls them forward through eternity. Five worlds. 5 different mechanisms of planetary death. Glass rain at hypersonic velocities. Temperatures exceeding most stars. Evaporating lava oceans. A planet feeding itself to its star. Corpses orbiting a lighthouse of radiation, each one discovered through meticulous observation. Each one confirmed through independent verification. Each one real. These are not the most dangerous planets that exist. They are simply the most dangerous planets we have found so far. The distinction is critical. Our detection methods are biased toward finding large planets in close orbits, hot Jupiters, super-Earths baking under stellar radiation. We have barely scratched the surface of planetary diversity. Every year, new telescopes come online, new detection techniques are developed, new worlds are discovered, and many of them are nightmares. The James Webb Space Telescope, launched in December 2021, has already begun detecting atmospheric compositions on exoplanets with unprecedented precision. It can identify individual molecules, measure temperature profiles, map atmospheric circulation patterns. Every observation reveals new extremes. Planets with atmospheres made of vaporized quartz, worlds where titanium condenses into clouds, gas giants losing their envelopes in real time. The European Space Agency's Plato mission, scheduled to launch in 2026, will monitor over 200,000 stars for 4 years, searching for Earth-sized planets in habitable zones, but it will also find countless worlds in non-habitable zones, planets too close, too far, too hot, too cold, too massive, too small. The catalog of dangerous planets will grow exponentially, and with each new discovery, the central truth becomes clearer. Earth is not the template, Earth is the aberration. Consider the statistics. Our galaxy contains approximately 200 billion stars. Conservative estimates suggest at least 1 planet per star on average. That means 200 billion planets in the Milky Way alone. The observable universe contains approximately 2 trillion galaxies. Simple multiplication yields 400 billion trillion planets, 4 times 10 to the power of 23 worlds. Of those incomprehensible numbers of planets, how many are habitable? How many have liquid water oceans, breathable atmospheres, stable climates, and surface conditions compatible with life? Current models suggest less than 1%, possibly far less. The requirements are strict. The planet must orbit in the habitable zone. It must have the right mass to retain an atmosphere, but not so much mass that gravity crushes everything. It must have a magnetic field to protect against stellar radiation. It must have plate tectonics to regulate atmospheric carbon dioxide. It must have a large moon to stabilize axial tilt and prevent wild climate swings. Each requirement eliminates the vast majority of planets. The habitable zone is narrow. Most planets orbit outside it. Most rocky planets lack magnetic fields. Most lack plate tectonics. Most lack stabilizing moons. When you multiply all the requirements together, the fraction of habitable planets drops to infinitesimal values. And even habitable does not mean inhabited. Venus is technically in the habitable zone. It is a hellscape. Mars was habitable 4 billion years ago. It lost its atmosphere. Being in the right location is necessary but insufficient. The planet must maintain habitability over billions of years while its star evolves, asteroids bombard the surface, and internal heat gradually dissipates. Earth has maintained habitability for 4 billion years. This is not normal. This is not typical. This is a statistical outlier so extreme that it might be unique in the observable universe. We do not know if other planets have achieved this. We have not found any. Every exoplanet we examine closely reveals deal-breaker problems. Too much radiation, wrong atmospheric composition, unstable orbit, tidal locking, extreme temperature gradients. The dangerous planets we have explored in detail represent the norm. They show us what planets typically look like, and what they look like is hostile, violent, lethal. The universe is not empty, it is full of worlds. But those worlds are not homes, they are hazards. HD 189733b teaches us that atmospheres can weaponize themselves. That weather can become a planet-wide industrial accident operating at hypersonic velocities. That beauty, the pale blue color, can mask absolute lethality. The planet looks like Earth from a distance. It would destroy any visitor in seconds. Kelt 9b teaches us that planets can be hotter than stars. That matter can exist in states we barely understand, that worlds can evaporate, shedding thousands of tons of atmosphere every second while spiraling toward inevitable disintegration. The planet is dying in real time. We are watching it happen, and we can do nothing but take measurements as it crosses year by year toward annihilation. Korat 7b teaches us that solid ground is not always solid, that surfaces can melt into global oceans of lava that never cool, that atmospheres can be made of vaporized rock, that planets can rain stone and snow glass, and weather systems can operate through phase transitions of minerals. The planet has redefined what we mean by weather. It rains rock. The forecast never changes. WASP 12b teaches us that orbits are not eternal, that planets can spiral toward their stars, doomed to be consumed, that mass loss is not always gradual, that worlds can feed their stars, slowly committing suicide, losing billions of kilograms per second while astronomers measure the exact date of destruction, 10 million years. The sentence has been passed. The execution is scheduled. The planet waits in its cell, unable to escape. PSRB 1257+12 teaches us that planets can survive stellar death, that worlds can form from the ashes of supernova explosions, that planetary systems can orbit corpses, that radiation can be so intense it sterilizes matter to the atomic level. These 5 worlds are lessons in cosmic hostility. They are data points in a larger pattern. And the pattern is clear. The universe creates planets as byproducts of star formation. It does not optimize for habitability. It does not design for life. It follows the laws of gravity and thermodynamics, and those laws produce mostly uninhabitable worlds. Planet formation begins in molecular clouds, cold, dark regions of space where gas and dust accumulate. Gravity pulls the material together. The cloud collapses. As it collapses, it spins. Conservation of angular momentum causes the spin to accelerate. The collapsing cloud flattens into a disk. That the universe builds planets in environments where life is impossible by definition. They are warnings written in radiation and gravity. Proof that planet formation is a mechanical process, not a teleological one. The universe does not create planets as homes. It creates them as inevitabilities. As consequences of rotating gas clouds and gravitational accretion, whether those planets can support life is irrelevant to their formation. The pulsar planets orbit in darkness. They will orbit forever. They are fossils of a catastrophe, remnants of an explosion, worlds born from death. And they teach us that the galaxy is filled with places where the ground is solid, the planets are real, and life is categorically impossible. The lighthouse rotates. The beams sweep through space. The planets orbit in silence, and the corpse at the center pulls them forward through eternity. 5 worlds. 5 different mechanisms of planetary death. Glass rain at hypersonic velocities. Temperatures exceeding most stars. Evaporating lava oceans. A planet feeding itself to its star. Corpses orbiting a lighthouse of radiation. Each one discovered through meticulous observation. Each one confirmed through independent verification. Each one real. These are not the most dangerous planets that exist. They are simply the most dangerous planets we have found so far. The distinction is critical. Our detection methods are biased toward finding large planets in close orbits. Hot Jupiters. Super-Earths baking under stellar radiation. We have barely scratched the surface of planetary diversity. Every year, new telescopes come online. New detection techniques are developed. New worlds are discovered. And many of them are nightmares. The James Webb Space Telescope, launched in December 2021, has already begun detecting atmospheric compositions on exoplanets with unprecedented precision. It can identify individual molecules, measure temperature profiles, map atmospheric circulation patterns. Every observation reveals new extremes. Planets with atmospheres made of vaporized quartz. Worlds where titanium condenses into clouds. Gas giants losing their envelopes in real time. The European Space Agency's Plato mission, scheduled to launch in 2026, will monitor over 200,000 stars for 4 years, searching for Earth-sized planets in habitable zones. But it will also find countless worlds in non-habitable zones, planets too close, too far, too hot, too cold, too massive, too small. The catalog of dangerous planets will grow exponentially, and with each new discovery, the central truth becomes clearer. Earth is not the template. Earth is the aberration. Consider the statistics. Our galaxy contains approximately 200 billion stars. Conservative estimates suggest at least one planet per star on average. That means 200 billion planets in the Milky Way alone. The observable universe contains approximately 2 trillion galaxies. Simple multiplication yields 400 billion trillion planets. 4 times 10 to the power of 23 worlds. Of those incomprehensible numbers of planets, how many are habitable? How many have liquid water oceans, breathable atmospheres, stable climates, and surface conditions compatible with life? Current models suggest less than 1%, possibly far less. The requirements are strict. The planet must orbit in the habitable zone. It must have the right mass to retain an atmosphere, but not so much mass that gravity crushes everything. It must have a magnetic field to protect against stellar radiation. It must have plate tectonics to regulate atmospheric carbon dioxide. It must have a large moon to stabilize axial tilt and prevent wild climate swings. Each requirement eliminates the vast majority of planets. The habitable zone is narrow. Most planets orbit outside it. Most rocky planets lack magnetic fields. Most lack plate tectonics. Most lack stabilizing moons. When you multiply all the requirements together, the fraction of habitable planets drops to infinitesimal values. And even habitable does not mean inhabited. Venus is technically in the habitable zone. It is a hellscape. Mars was habitable 4 billion years ago. It lost its atmosphere. Being in the right location is necessary but insufficient. The planet must maintain habitability over billions of years while its star evolves, asteroids bombard the surface, and internal heat gradually dissipates. Earth has maintained habitability for 4 billion years. This is not normal. This is not typical. This is a statistical outlier so extreme that it might be unique in the observable universe. We do not know if other planets have achieved this. We have not found any. Every exoplanet we examine closely reveals deal-breaker problems. Too much radiation, wrong atmospheric composition, unstable orbit, tidal locking, extreme temperature gradients. The dangerous planets we have explored in detail represent the norm. They show us what planets typically look like. And what they look like is hostile, violent, lethal. The universe is not empty, it is full of worlds. But those worlds are not homes. They are hazards. HD 189733b teaches us that atmospheres can weaponize themselves, that weather can become a planet-wide industrial accident operating at hypersonic velocities, that beauty, the pale blue color, can mask absolute lethality. The planet looks like Earth from a distance. It would destroy any visitor in seconds. Kelton IB teaches us that planets can be hotter than stars. That matter can exist in states we barely understand. That worlds can evaporate, shedding thousands of tons of atmosphere every second, while spiraling toward inevitable disintegration. The planet is dying in real time. We are watching it happen. And we can do nothing but take measurements as it crosses year by year toward annihilation. Qurat 7b teaches us that solid ground is not always solid, that surfaces can melt into global oceans of lava that never cool, that atmospheres can be made of vaporized rock, that planets can rain stone and snow glass, and weather systems can operate through phase transitions of minerals. The planet has redefined what we mean by weather. It rains rock. The forecast never changes. WASP 12b teaches us that orbits are not eternal, that planets can spiral toward their stars, doomed to be consumed, that mass loss is not always gradual, that worlds can feed their stars, slowly committing suicide. losing billions of kilograms per second while astronomers measure the exact date of destruction. 10 million years. The sentence has been passed. The execution is scheduled. The planet waits in its cell, unable to escape. PSRB 1257+12 teaches us that planets can survive stellar death, that worlds can form from the ashes of supernova explosions, that planetary systems can orbit corpses, that radiation can be so intense it sterilizes matter to the atomic level. These 5 worlds are lessons in cosmic hostility. They are data points in a larger pattern. And the pattern is clear. The universe creates planets as byproducts of star formation. It does not optimize for habitability. It does not design for life. It follows the laws of gravity and thermodynamics, and those laws produce mostly uninhabitable worlds. Planet formation begins in molecular clouds, cold, dark regions of space where gas and dust accumulate. Gravity pulls the material together. The cloud collapses. As it collapses, it spins. Conservation of angular momentum causes the spin to accelerate. The collapsing cloud flattens into a disk. At the center, pressure and temperature increase until nuclear fusion ignites. A star is born. The disk contains the raw materials for planets. Dust grains collide and stick together through electrostatic forces. The grains grow into pebbles. Pebbles grow into boulders. Boulders grow into planetesimals, mountain-sized objects held together by gravity. Planetesimals collide and merge. Eventually, a few dominant bodies emerge. Planets. This process is mechanical, deterministic. It follows physical laws without exception. The laws do not care about habitability. They care about mass, gravity, temperature, and angular momentum. The result is a planetary system whose architecture depends on initial conditions and random chance. Some planets form close to the star where temperatures are high. These become rocky worlds. But if they form too close, they become lava worlds. Some form far from the star where temperatures are low. These become gas giants or ice giants, but if they migrate inward through gravitational interactions, they become hot Jupiters, spiraling toward eventual destruction. Most planetary systems are unstable during their formation. Planets gravitationally scatter each other. Some are ejected into interstellar space. Some collide and merge. Some spiral into the star. Some are left in stable orbits. The survivors are not the best. They are simply the lucky ones that happen to avoid catastrophe during the chaotic early phase. Our solar system is the result of this process. We had luck. Jupiter formed at the right distance to act as a gravitational shield, deflecting asteroids and comets that would otherwise bombard Earth. Saturn stabilized the outer system. The Moon formed from a giant impact that ejected material into orbit, later accreting into a single body large enough to stabilize Earth's axial tilt. Mars formed small and lost its atmosphere. Venus experienced a runaway greenhouse effect. Mercury was stripped down to its iron core by solar radiation. Earth survived. We survived. But survival does not mean we are safe. It means we have not yet encountered the catastrophe that will end habitability. Earth's habitability has an expiration date. In approximately 1 billion years, the sun will brighten enough to trigger a runaway greenhouse effect. The oceans will evaporate. The atmosphere will be stripped away by solar wind. Earth will become Venus. The planet will remain, but life will be extinct. This is the inevitable fate of all planets orbiting main sequence stars. Stars evolve, they brighten as they age. Eventually, they exhaust their hydrogen and expand into red giants. When the sun becomes a red giant in 5 billion years, it will expand to Earth's orbit. Earth will be engulfed and vaporized. The planet will cease to exist. The debris will be incorporated into the sun's outer layers. Mars will survive longer because it orbits farther out, but it is already dead. Mercury will be consumed first. Venus will follow. The outer planets will become warmer, briefly, before the sun sheds its outer layers and collapses into a white dwarf. The solar system will become cold and dark. Jupiter's moons might experience a brief period of habitability as the sun brightens, but it will not last. This is the fate of all planetary systems. Stars die, planets are destroyed or left orbiting cold stellar remnants. The universe creates planets, waits a few billion years, then destroys them. The cycle is universal. The outcome is inevitable. Planets are temporary structures. Their habitability, if it ever exists, is even more temporary. And this brings us to the uncomfortable philosophical implication. If planets are temporary and habitability is rare and fleeting, then life itself might be a cosmic accident. A brief, localized phenomenon that arises occasionally when conditions happen to be right, then vanishes when conditions inevitably change. We exist because Earth happened to form in the right location, with the right mass at the right time around a star of the right type. Change any one of those variables, and we do not exist. If Earth had formed 5% closer to the Sun, runaway greenhouse effect. 5% farther, permanent ice age. If Jupiter had not formed or had migrated inward, asteroid bombardment would have prevented complex life. If the Moon had not formed, unstable axial tilt would have caused climate chaos. We are here because of a chain of coincidences so improbable that it might not have occurred anywhere else in the observable universe. And even if it has occurred elsewhere, those civilizations face the same ultimate fate. Their stars will evolve, their planets will be destroyed, their existence will end. The dangerous planets are not anomalies, they are the standard. They show us what planets typically look like. Worlds where the surface is molten, where the atmosphere is toxic, where radiation is lethal, where orbits are unstable, where temperatures are extreme. These are normal planets in a universe that does not care about life. Earth is the anomaly. Earth is the outlier. We are the statistical fluke, and we exist on borrowed time, orbiting a star that will eventually destroy us. On a planet whose habitability will expire long before the star becomes a red giant. This is not pessimism. This is physics. This is thermodynamics. This is astronomy. The data are clear. The measurements are precise. The conclusions are unavoidable. The universe is not hostile to life. Hostility implies intent. The universe is indifferent. It creates planets through mechanical processes that occasionally produce habitable conditions. When those conditions arise, life might emerge. But the universe does not sustain those conditions. It changes them, destroys them, moves on. We have found 5,000 exoplanets. We have examined dozens in detail. We have found atmospheres made of vaporized glass, vaporized iron, vaporized rock. We have found planets hotter than stars. We have found planets being eaten. We have found planets orbiting corpses. We have not found another Earth. The search continues. The telescopes improve. The detection methods become more sensitive. Perhaps we will find an Earth analog someday. A planet with liquid water, oxygen atmosphere, temperate climate, stable orbit. Perhaps such planets are common, and we simply have not detected them yet. But even if we find them, they will not be safe havens. They will be planets facing the same ultimate fate as Earth. Temporary oases in a universe of hazards. Brief windows of habitability in deep time. Places where life might exist for 1 billion years before stellar evolution makes them uninhabitable. The dangerous planets teach us humility. They remind us that our existence is contingent, that we are not the center of anything, that the universe did not make planets for us. It made planets because gravity pulls on gas clouds, and sometimes those gas clouds collapse into planetary systems. And very rarely those systems contain habitable worlds, and even more rarely those worlds develop intelligent life. We are temporary. Our planet is temporary. Our sun is temporary. Everything ends. But before it ends, we have time. Time to explore. Time to discover. Time to understand. We can point our telescopes at distant stars and measure the properties of their planets. We can calculate orbital parameters and atmospheric compositions. We can map the diversity of worlds. We can catalog the dangers. And perhaps, in that catalog, we will find not just horrors, but possibilities. Exomoons around gas giants that might be habitable. Rogue planets with subsurface oceans heated by radioactive decay. Worlds and binary star systems with complex but stable climates. The universe is vast. The possibilities are endless. Some of those possibilities might include life. But the dangerous planets will always outnumber the habitable ones. For every Earth, there are 1 million Kelt 9b's, 1 million lava worlds, A million pulsar planets. A million death traps masquerading as worlds. The universe has built a cosmic kill list, and we are reading it. Planet by planet, discovery by discovery, measuring the 1,000 ways that worlds can become prisons, ovens, radiation zones, and tombs. Earth sits on that list too, not at the top, not yet, but it is there, scheduled for destruction. The countdown has already begun. The clock is ticking. 1 billion years until the oceans evaporate. 5 billion until the sun engulfs us. The sentence has been passed. The execution date is set. We exist in the brief moment between formation and destruction. The narrow window where liquid water flows, air is breathable, and the ground is solid. We exist on the only known planet in the universe where these conditions have persisted long enough for intelligence to emerge. And what have we done with that intelligence? We have built telescopes, we have pointed them at the sky, we have discovered 5,000 worlds, and we have learned that we are alone on an island, surrounded by an ocean of death that stretches to infinity in all directions. The glass rain falls on HD 189733b. The lava churns on Korot 7b. The atmosphere escapes from Kelt 9b. The orbit decays on WASP 12b. The radiation blasts the pulsar planets, and Earth spins quietly in its safe orbit, temporarily shielded from the chaos, waiting for its turn. The universe is not empty. It is full of worlds. But most of those worlds are nightmares, and the few that are not nightmares will become nightmares eventually. That is the lesson of the 5 most dangerous planets. That is the truth written in spectroscopy and orbital mechanics. That is the message delivered by photons that traveled hundreds of light years to reach our telescopes. We are temporary passengers on a temporary world. The universe will outlast us. The planets will outlast us. Even the dangerous planets, being destroyed in real time, will outlast human civilization. And when we are gone, when Earth is a lifeless cinder or a cloud of plasma, the universe will continue creating planets. Some will be habitable for a while. Most will be hostile from birth. The process will repeat across trillions of galaxies for trillions of years. An endless cycle of creation and destruction. Planets forming, planets dying, no purpose, no meaning, just physics. The dangerous planets are waiting in the darkness. If you found this journey through cosmic horror enlightening, if you want to explore more worlds that defy comprehension and challenge our place in the universe, hit that like button and subscribe to Cosmic Chronicles. Because the universe has more nightmares to reveal, and we have only just begun to catalog them. The void is watching, the planets are waiting, and somewhere out there, a world is dying that we have not yet discovered.